Okay, good. So yeah, this afternoon, I want to touch on um, electricity, right? Electricity, right? And we're going to talk about for static electricity, right? And then we're going to talk about current electricity, right? And under current electricity, we're going to divulge into um, direct current, direct current, and then we'll look at alternating current, alternating current, right? We may not, I'm not sure if we can cover all of this. Um, I'm not sure we can cover all of this material in one afternoon, right? So we're going to see how much we can cover. So I want us to start with before we can actually get into um, electricity per se. Um, I want to get into, the structure of materials first. And then we will be able to understand, why we call one type of electricity static and the other one as current electricity, right? The reason why is that electricity basically has to do with the flow or the movement. Let me use the word movement because there are times when there isn't a flow as such, right? You might just have a situation where it includes charges that are at rest and can tend to move or cause things to behave a certain way, right? So electricity basically got to do with the movement of charges, right? Or charged particles. And before I can actually get into that, I probably have to get into what happens at a molecular level, right? What happens at a molecular level, or even I should say the atomic level as well, right? So there's something called insulators, insulators, right? And then there's something called conductors. So when you're dealing with, this is an R, right? Yeah. When you're dealing with electricity, you hear about these types of materials a lot. You'll hear about insulators and you will hear about conductors, right? And what really are these? What are insulators? What are conductors? Right? And here we're talking about um, insulators of electricity, right? And conductors of electricity. Because these can also refer to heat as well, right? Certain things are good insulators, right? In that they don't allow heat to flow across them freely. And some things are good conductors of heat in that they allow heat to pass freely. And in very many cases, you find that good thermal insulators are good, um, electrical insulators. Similarly, in terms of conductors, right? You find that materials that conduct or pass electricity very easily may also pass thermal energy or heat very easily, right? But remember, when we are talking about insulators here and we're talking about conductors here, um, we're talking about materials that, as we said, doesn't freely conduct or doesn't allow the free flow of electricity. When we speak of conductors, these are materials that cause, um, you know, for for things to freely, for electricity to freely flow, right? So before I get into all of that, I'd have to get into, what's going on at the, as I said, atomic level, right? Or the molecular level of matter, right? So let me borrow an image. I want to bring it over here just for you to see what's going on, right? All right. So, okay, yeah. So here is a model. Here is a model of the atom, right? And the atom is like the building blocks of all matter, right? So when we go down, if we were to divide matter up to its smallest pieces, right? We come down to what we call atoms, right? And atoms, as you see here, this is what you refer to as, these are protons, right? And these with the minus sign, you see these are electrons, right? So you have protons. Protons are positively charged, right? They have a positive charge, and electrons have a negative charge, right? Um, this here is what we refer to as the nucleus, right? I have to go slowly. This is the nucleus of the atom. And in the nucleus of the atom, there is another particle name. They refer to them as neutrons, right? Neutrons. And those don't carry a charge. They don't carry a charge, right? So we're not going to include them in our model, right? Because with respect to, conducting electricity or not conducting electricity, proton is not going to be important to our discussion, right? So don't go and tell people, Mr. Ghani, show us a model of the atom and his atom don't have any proton inside, right? Uh, for our sakes, we are more concerned about, what we call protons in the nucleus, and more importantly, electrons that kind of orbit the nucleus. Well, let me put it randomly, right? Randomly. There is a way, those who study what they call quantum mechanics and so can say that you can actually predict where the electron is going to be at a particular instant of time and all of that. We're not ready for that, right? We just want to get an idea of what goes on at the atomic level and what makes some materials, freely conducting in terms of electricity, while others do not, right? And yes, so when you have several atoms interacting with one another, and I want to bring another, model for you to see, right? So as atoms interact with one another, okay, yeah. As atoms interact with one another, ever so often, you can have a situation where electrons somehow got dislodged from its orbit, right? It got dislodged. And indeed, these things are spinning very, very fast, right? And it is possible that in all this, the interaction with one another, that electrons can get bumped out of, let's say it was here, and it get bumped off and it goes over there, right? It can happen. As a matter of fact, those who study metals, they are of the theory, right? And remember all of these things. We can't see we can't see what's going on at the atomic level. So what we do is we try to model what's going on in materials based on how they behave, right? So look here. So what I believe is going on in metals is that the outer electrons of the atoms are actually like they're free to be shared among atoms. So they say that these electrons, they're free flowing in metals, right? Metals such as, aluminum and steel and gold and so these metals, they kind of allow their electrons to flow freely around it, right? And for that reason, when what you call a potential difference, I know I'm introducing all these, something called a potential difference in that if this was a piece of metal and the potential difference between here is, let's say, down here is positive and down here is negative, what will happen is that these electrons will tend to flow. I think I should have put it the other way around. Let me, based on this arrow that is here, let me put, let's say there's a potential difference where this side is positive, or I should say more positive than this side, which is negative, right? So what happens now, there will be a tendency for these electrons to flow towards the positive side, right? So if the potential difference here is positive and here is negative, these electrons will tend to flow towards the positive side, right? So once we create that, we call potential difference, right? Electrons will tend to flow. The difference with insulators, right? And I probably want to just give me a second. I want to bring a diagram of what goes on in an insulator, right? Give me 1 second. It's not allowing me to copy. Why is that? All right, let me snip it. Huh, that's strange. I want to bring a diagram of the kind of structure you see inside of insulators, just to show you a contrast, right? Oh, all right, look here. Good. So ignore this part about static electricity. We just want to look on top here, right? So what you find happening in insulating materials, right, is that the electrons are strongly bonded to the nucleus, right? Yes, there are times, as you see here, where electrons are shared, right? For example, like if you have a oxygen molecule, right? Oxygen is one oxygen is here, right? And these electrons are going around it. And they actually would share, they would actually share, maybe I think it's 2 electrons they share, right? Here, they share 2 electrons. And those 2 electrons that are in the middle here are tightly bonded in the molecule. So these are 2 atoms, and they somehow come into a kind of bonding in chemistry. There's a special name for them, right? And they call it molecular bonding, right? So the electrons are tightly, they're held on strongly, right? And as you see here in this other part of the picture here, right? The bonds, the material is arranged in such a way, right? Where the atoms are you know, they have a strong bond, and it doesn't allow electrons to flow easily. It doesn't allow electrons to flow easily, right? So unlike metals such as iron and copper and aluminum and so, they have what you call metallic bonding. And they actually give up their outer electrons and let it be like in the textbooks you hear they talk about a sea of electrons ready to be moved around based on, you know, potential difference that is created across the end of the metal, right? But in insulating materials, the electrons are, you know, they're held in between there, right? And they're not easily given up. Notice I said not easily given up. It's not impossible to move them around, right? But it's very difficult to do so, right? So that is what makes an insulator an insulator, right? In the case of insulating materials, there aren't too many free electrons to flow around the place, right? Flow around the material. The electrons are strongly bonded to the nucleus, right? And the entire structure of the material is such that it doesn't allow, like you see here, right? They speak of strong bonds, and there isn't place for electrons to be flowing around. Whereas the one with the metal, look at the metal. Time to go back to the metal. Go back, where is it? Look at the metal. The metal, the electrons are given up and they're all floating around there. Any least potential difference applied to it, they're ready to move. They're ready to move, right? So with this little understanding of what goes on at the atomic and the molecular level of conductors and insulators, we are now in a position to at least have a basic understanding of what happens, you know, when a potential difference is applied to them, right? So we'll start with what we call static electricity. And that's what we are talking about here. Static electricity. We start with that. And I think many of you are familiar. Many of you are familiar with, I don't know if you did this in school. You take your pen, right? You take your pen and you rub it against your hair or your pants, right? And you chip up some paper. You chip up some paper and you put it on the desk. And guess what? When you take the pen now, you put it near the paper, it picks it up like a magnet. Anybody ever did that little experiment in school?
Yes, sir.
Yes, that I remember when we were kids, we would do it a lot. You rub the pen on your pants or your short. Some people do it with their hair, right? And then you take some little pieces of paper and you take the pen and you bring it near the paper and it picks it up like a magnet. And you want to know what miracle have you done there, right? Well, what's happening there? And as you see in this picture here, right? When you rub, let's say you have a rod, right? And this is, let's say, a polythene rod. You know, polythene is like a plastic rod. Let me go with a plastic rod. And you take a cloth and you rub it, you rub it, you rub it. What will happen is that one of them will become positively charged, while another one will become negatively charged, right? And when that happens, right? When that happens, um, the difference in charges makes it possible now for you to actually attract other materials. Because what would happen? Let me just see if I can um, trying to see if I can get a picture of. Give me 1 second. I want to see if I can get a. Um, yeah, I want to get a picture here of what I just described to you there. No. Yeah, look here. So you take the cloth and you rub the rod, you rub the plastic rod. And what happens now is that the rod becomes negatively charged. And the reason why is that some electrons from the cloth, that vigorous rubbing is like you give it enough energy to jump over, right? Granted, these are two insulators. The cloth is an insulator, the rod is an insulator. However, there are some electrons that, given enough energy, you can actually pluck them out, right? And they can be transferred from one material to the next, right? And what can actually happen, right, is that the rod becomes negative, the cloth becomes positive, right? And as a matter of fact, if you bring them close, they will tend to attract one another, right? They'll tend to attract one another. What can also happen is that, and that can cause attraction. Let me show you another picture, right? It's true that these things happen at the atomic level, so you don't know. As a matter of fact, this is the subatomic level now, right? Let me give you an example. No. Yeah, look at this here. So this is like a balloon, and maybe because of your hands, and so you rub a balloon, and so, right? It becomes negatively charged. So when you bring it against another insulating material, let's say this is a glass wall or some kind of wall, right? What happens, because the balloon is negatively charged, it will repel at force, right? It will repel the electrons in the wall to kind of move away from this edge here. And because there's a positive charge here and there's a negative charge there, the balloon can go and kind of pace up there. I don't know if you ever see this or this happen to you. You ever notice you lose balloon and the balloon like to go and hug up and against a wall? And you want to know what is the love affair going on there? Well, it's because of these charges, right? The balloon got negatively charged, right? When it goes near the wall, it does this. It kind of repels the electrons more inward. And now there's some positive charges here that creates an attraction. And the balloon might very well go there and stick up, right? And then if you want to know why is the balloon sticking up there, right? Yeah. So that explains, these little things, what we call static electricity, right? Static electricity. In that it doesn't involve a flow of electricity, right? These are just charges that are, there's not much movement of them, right? Any movement is just at the atomic level, right? Not much movement is happening where current flows from one place to another. No, this is just okay. The electrons are just dislodged, and remember, this is an exaggeration, right? The electrons are moved just maybe nanometers away, right? Very small movements are happening. So there's no big flow of these electrons to create the kind of current you see when we deal with conductors, right? So now that we are introduced to static electricity, we see static electricity in real life a whole lot. And before we go away from it, I just want to talk about what we call electric fields. And you'll see why I want to talk about it, because it has a lot to do with safety, right? Let's talk about electric fields a little. Electric fields. Let me see if I can. Give me a second. Oh my, yeah. All right. Yeah. So let's say this is a positive charge, right? Let's say it's a positive charge. And let's say this is a negative charge, right? What really happens? Let me explain what they are saying is an electric field. An electric field basically is like an invisible area, like it's an area around a charge, right? Where that charge is going to exert a force on other charges around it, right? So keep that in mind. An electric field is basically it's an area around a charged particle where a force is exerted, right, on other objects that are in the field, right? So if you have something, or like here, you have a negatively charged particle here, it will tend to attract it, right? Force will um, kind of act on this negative particle to pull it towards the positive particle, right? Here you see the opposite. If there's a positive particle here, right, this negative charge here is going to pull it towards it, right? And I just showed you where you can have somewhere that a body that is neutral. It's not negative or positive. But what will happen is that this charge can create a kind of polarization, right? As we saw just now. Let me just go back. Let me go back to the balloon and the wall. Watch here. Initially, this wall was nice and neutral. But because you bring this balloon close to the wall, it causes a certain kind of, I'll use the word polarization, meaning it kind of creates some positive or negative, poles then, right? All the negatives are repelled there, right? And all the positives are attracted there. Now that makes this body attracted to the balloon or the other way around. The balloon is now attracted to the wall, right? And that's how electric fields work, right? Let me give you a diagram where you have like, okay, let me show you when you have similar fields, you would have repulsion. I just talked about attraction just now, but you can have, oh my, yeah, you can have repulsion happening. Like when you have two positive charges, they're going to repel one another. When you have two negative charges, they're going to attract one another. Sorry, what am I saying? Once the charges are the same, they'll repel one another. Positive and positive, they'll repel. Negative and negative, they'll repel one another. Just like the poles of a magnet, right? North and north don't attract one another, they repel. But if the poles were similar, different, one is positive, one is negative, they'll attract one another. If one was negative, one was positive, it will attract one another. As you saw down here, like these two will definitely attract one another, right? But when they're different, when they're the same, right? They're going to repel one another. Good. Now, why am I? Oh my, you did something. Oh, yes, I lost my screen there for a moment. Yeah. All right. Yeah. So, why am I talking about static electricity? Right? Why am I talking about static electricity? Because static electricity, y'all give me 1 second. I'm noticing that this bulb is, oh gosh, my bulb went. Give me 1 second. Let me pause the recording. Yeah. Why am I talking about static electricity? I mean, both types of electricity, they have their risks, right? And their dangers. And static electricity in particular can cause a lot of problems in everyday life, right? And one of the things that, well, I'm going to use this word. Let me make this a little bigger. I'm going to use this word very loosely. Sparking. Now, let me tell you what's really going on when you see. Have you ever like, you take a battery, right? You take a battery and the battery lug is here. And sometimes you take a piece of wire and sometimes you're not touching the battery yet and there's a spark jump across there. Have you ever seen that happen? You didn't actually touch the battery yet and there's a spark that jumps across. Has that ever happened to you? Anybody ever had that experience? Sparking? All right. Y'all have very limited experience in this life. All right. We're all familiar with lightning, right? Is the class with me? I just want to know if I
Yes,
lost
sir.
them. Yeah, say something, man, so I'll know you're there. Yeah. Everybody is familiar with lightning, the whole world over. Well, lightning is basically what you see when you take a conductor, like, and you bring it close to a battery lug, and you have arcing taking place. Arcing. Okay. Anybody here, you ever observe people welding?
Yes, sir.
The man is welding, and here's the rod. But the thing he is actually using to weld, right? He doesn't paste it onto this metal, he brings it very close. He brings it about a couple away from the metal. He brings the welding rod very close. And what happens, because this welding rod is a very high voltage, right? Let me say a couple thousand volts, right? Let me say 1,000 volts. And they normally, if you're welding this thing, you connect this thing to the ground. You all know that, right? You clip on something onto the rod, and this is connected to the ground. So the voltage here is 100, and let's say the ground here is 0, right? Good. So what happens now, because of this big, we call potential difference, right? Here is 1,000 and this is 0. I'm just using a number 0, right? Because of that difference, what happens is that there's sparking, there's arcing. They use the word arcing, not sparking. They use the word arcing, and there goes the name arc welder, right? It's actually a spark jumping across, right? Or an arc jumping across, right? What's happening here is that because of that arcing, the metal heats up and this rod heats up and it melts the rod, and that is what welds the thing, right? Good. Now, what's really happening, and the same thing is really happening when there's lightning, right? Let me explain what happens when you have lightning. So clouds are moving around, a lot of wind and so. And because of all of that movement, you sometimes have, okay, one cloud end up being overall, let's say, positive, right? You can have that. And sometimes you can have a cloud that is negative, right? So regardless of what happens, and okay, let's take the ground. All right, let me go with the ground. Lightning, okay, there's this cloud up there that because of its blowing around and rubbing against one another, the cloud becomes so positively charged with respect to the ground. So let's say, okay, down here is 0 charge, right? What happens now is that the large positive charge here, and let me go with, even if you want to take this as negative. So the air between here, so let's say, all right, you have air particles here, right? Positive, negative, right? Positive, negative. Now, what happens is that the positive charge is going to be attracted to this negative, and the electrons are going to be attracted there. So what will happen? The large negative charge is going to tug at the positive part of the air molecules in the air. And the large positive charge is going to tug at the negative electrons in the air molecules. And what will happen is that it will tear it apart, right? It will cause what you call ionization, right? In that it will break up this air into positive ions and negative electrons, right? So, Art, I think I did it wrong. The negatives are going to shoot towards there, and the positives are going to shoot towards there, right? And because of that ionization, right, and this entire process, there's a lot of heat, right, and light being generated, and the end result is a big jump, and that's what you see as lightning. So it's the cloud really, because one cloud becomes very, very positively charged, thousands of volts, right, and another part becomes negatively charged, maybe minus 1,000 volts, right? You can also have that happening between a positively charged cloud and the Earth, and a negatively charged cloud and the Earth as well. And what it does, all the air molecules in between here is ripped apart. It ionizes the air, right? And all the electrons fly up to the cloud, right? And all the positive go towards the ground, right? Same thing here. All the electrons go towards the positive cloud. All the positive charge or the protons fly towards the negative cloud. And that creates that big spark and that big explosion. You hear thunder and you see lightning, right? That's what's going on. So that's what happens on a small scale when you're welding, right? When you are welding. And therefore, because of the power of static electricity, we have to be very, very careful, right? Of course, it has its benefit for those of you who don't know, right? Take, for example, lightning. What lightning does in the air, it actually splits nitrogen, right? For those of you who don't know that, right? I think I have a picture here. I should have shown you. Let me before I go there, let me show you the picture here. I do have a picture that I can bring across. 1 second. Yeah. Yeah, look here. So if you have a very negative charge here and a very positive charge, remember we said that around these charges, there's going to be an electric field, right? A force tugging at whatever is in between. And if these two things are very close, well, they exaggerate it for you to see, right? What will happen as you see here? Watch what is happening here. You have oxygen, you have nitrogen in the air, and what will happen? It will actually break up the oxygen and break up the nitrogen molecules in the air, right? So it's actually going to ionize it, right? And as you see here, all the positive charge is going to go towards, well, the positive is going to go this way, right? Where the negative is, and the negative is going to go where the positive is, right? And that's what you and I see as a big spark. When lightning flashes, when the arc is struck for welding and all of that, right? Yeah. And there are some benefits of that, like, okay, in arc welding, without that, we can't have arc welding, right? I've actually seen, by the way, I've seen a lighter where it works on this principle, right? I've seen a lighter, the Chinese sell it. Let me just give you a diagram of what it looks like. So the lighter is, okay, this is the lighter here, right? And on top here, it got some sprung, like 4 sprung, right? 4 sprung. And what the little electronics in here does, it actually raises this point here to let me say, all right, let me say 500 volts, right? and maybe the other one is just 0 volts, right? And because of this potential difference, this is 0 and this is 500, right? Or they can actually make this negative if they want, right? I don't know the exact voltage there, right? So, but because of this big voltage difference, what happens? It ionizes the air here. So when you press the lighter to light it, it actually is a spark jumping across there. And any boy in this class who is a smoker actually have one of those lighters. I'm not talking about the one that where you click the thing and the thing there's this carbon and I don't know it's phosphorus or what, and you actually get a flame ignited because there's a fuel inside. No, this is a purely electrical lighter where between the points, they have 2 points light, right? One is very positive, the other one, let's say, is negative, right? It can be 0 as well. And because of this little gap that is there, the thing flies across, right? There's an arcing between here. And when that arcing takes place, it can light a cigarette, it can light your stove. So those are some good use cases of static electricity, right? There are plenty of use cases. I'll send you some notes where they will explain that when you do photocopying and printing, and those of you who are into agriculture, the chemicals actually, they're given a charge. So when you spray them, they kind of go out and spread out. I don't know if anybody here is into agriculture. You notice how when you pump that can and you spray out the chemical, how it goes out like a fine mist? It's because in the can, you do a kind of charging, right? You charge up the particles. And when the particles go out, because they are all of the same charge, they kind of spread out in a nice swath. And it also explains why the chemical go and stick onto the leaf of the plant, right? So those are positives, right, of static electricity, right? Let me give you a last one since there's a lot of rain and lightning and so right now. When lightning, as you can see here, you're seeing nitrogen, you're seeing N, N2 and all of that, right? When lightning strikes, right? Or in other words, when lightning ionizes the air, what actually happens, right? The nitrogen is broken up, right? They're broken up, and it combines with oxygen into something called nitric oxide, right? And when it interacts with rain, so nitric oxide mixed with rain becomes nitric acid. And when that falls to the ground now, it actually would react with, whatever is happening in the soil, and it forms nitrates. In other words, lightning gives us free fertilizer. That explains why rainwater grows things so well. You water plant with the chlorinated water, the plant ain't growing. But when rain fall, everything just sprout up. You ever wonder why? It's because when lightning strikes, right? When there's ionization taking place in the atmosphere, the nitrogen is broken up, it mixes with oxygen, then water, and then it falls to the ground, right? As rain, and it actually goes into the soil and fertilizes the soil, right? So it's free fertilizer then, natural fertilizer, right? Yeah. Yeah. However, you can have situations where ionization or this static electricity creates some problems. It can cause fires and so, right? I think, give me 1 second. Let me see if I can find some. I'm trying to see. Okay, yes. So because static electricity is so dangerous, you have to be careful that flammable liquids they're not near, right? because of yeah, I'll be back. Yeah, somehow I got bumped off the internet. Yeah. Anybody here ever when they touch their car, let's say their car windscreen, they get a little shock? Or sometimes you jump into your car, and some of you, your cars, you slide from end to end. And then when you watch the hair on your hand, it actually kind of attracted to the leatherette or so in the car. You ever notice that? Or sometimes if you have a sofa at home and the sofa is made of leatherette and you slide on it, right? And if your hand goes near the material, it actually causes your hair to stand up. You ever notice that thing? Anybody?
Yes, sir.
Yes, that can actually um, you can actually have a little shock as well, right? And that is why places like gas stations and so, right? They don't want you to go smoking around there and so, right? But besides that, you can have static electricity building up on your vehicles, right? And what needs to happen now is that you would have to have some kind of grounding so that there's no spark, right? There's no spark to cause a fire like at gas stations, right? So you can do a lot of things, right? If they have like a part, let's say, all right, I'm just saying, I don't know if any one of you, you're working at a place where there's a conveyor belt, and on this conveyor belt, it could be, all right, let's say even if there's a pipe, right? And some fluid is flowing through that pipe. Over time, that fluid flowing through this pipe can build up a charge in here. It can build up a charge, right? Inside there. And what can happen? Because this pipe is now very, very charged up, out here, let's say this is zero, right? The potential difference here is zero. And down here is positive, right? You can have a spark jumping across. So what they'll do, they'll ground this pipe somewhere. Somewhere they'll connect this pipe to the earth with some grounding wire, right? They'll have a grounding wire there. So that any charge that builds up in this pipe, well, it will discharge itself to the ground, right? You'll find that if there's a grain, let's say there's a pipe or there's some chute, that grain is sliding through, maybe rice, it's sliding through. What will happen? Over time, a charge will build up, right? And if that charge is large enough, it can cause sparks, right? Some of you don't see the spark. But if there's flammable, let's say on the ground here, somebody spills some fuel, diesel, gasoline, kerosene, waste oil, you can have a spark and it ignites this and it causes a fire, right? So I'll send you some notes as to some safety precautions that we need to take, right? And some use cases of static electricity. I don't know if any one of you in your house, you have these ionizers that will actually collect dust out of the air. What it is a little tower-like. It's a little tower, right? And inside there has a charge rod, right? And the rod might be, let's say, positive, right? Very positive to a high charge, right? And air particles, what this thing does, it sucks in, right? So you got some vents and so, right? You got some vents, and there's something pulling in air. And as the air pass through and go out, any dust in the air, go and stick up around there. It go and stick up around here. And periodically you'd have to open this thing and you take this rod and you clean it out. You can clean it out with a moist cloth, right? And that keeps your home clean. Anybody has that at home? So there's some good use cases of it, but then there's some dangers of it as well, right? There's some dangers of it. Lots of places. I remember in Singapore, they're building an island where what they're doing is that they're taking all the garbage. And if you all know anything about Singapore, right? It's a very, very clean place, right? It's a very, very clean place. As a matter of fact, in Singapore, if you're caught littering, the police will beat you publicly. They'll beat you. They don't care if you're a tourist and all, they beat you. I'm not joking. That's a rule, right? So they take their garbage and they make electricity. But you say, man, but burning garbage creates a lot of smoke with a lot of nasty dust and so. So what they do, they have these chimneys, like, right? And in the chimneys, they'll have these rods, like, I'll just draw one. So the smoke going up there, But this rod, let's say they charge it, positive charge, strong positive. So as the air goes in there, sometimes they don't have one, they probably have 4 of them, right? And all the dust particles is going to go and stick up there. Sorry. The dust particles, I'm putting plus sign for some reason. They're going, and of course, periodically, they'll have some system to scrape off this dust. And they carry it and throw it into landfills, right? As a matter of fact, they're building an island off Singapore with the ash and all this dust and so that comes out of the chimney. So it doesn't, if dust don't go out, they'll have a lot of gases, yes, right? But they'll actually make sure that the dust particles in this smoke actually sticks on here. Not all of it. I mean, some of it has to go out in the air, but they maintain it so that the level is very, very low, right? So while it has its good uses, right? I can go on and on and on and talk about static electricity being used in, I mentioned the photocopier, printing, and so they use it. But at other times, right, as I said, once there's, you have an insulating material, right? And, sometimes you might have a chute and grains are flowing down this chute, right? So maybe, let me say rice coming down there, right? Rice coming down there. What will happen as the rice, flows along here? It's going to cause a charge to build up here, right? And over time, if this chute is not somewhere, they'll put a metal coating somewhere and ground that metal coating, right? So that these charges are going to, from time to time, flow down to earth. So no way can we have a spark going down to the ground. And maybe if you have something flammable, cause a fire, So grounding is very important. Like aeroplanes. When aeroplanes, they fly through the air, the aeroplane has a very, very large charge built up on its surface, right? So as the airplane flies now, when it comes to landing, guess what? Sometimes the wheels of the airplane is conductive. It takes the charge away from the airplane. In some instances, they have a little chain hanging out somehow from the airplane, and as soon as it hits the ground, the chain starts to drag on the ground, all the charges, let's say the airplane charge up, plus, very strong charge, right? they allow it to go down to the ground, right? And the airplane is discharged. Can you imagine if the airplane has a large positive charge, and then they say, "Oh, let me go and fuel up this plane body." You know, when they take the fuel close now, this charge jumps over, right? So there's a big spark, and you got airplane fuel right there. What happens? You see? So they'll have a way, right? And as I said, different different times and different manufacturers find ways of ensuring that the airplane body is discharged, right? Whether be it through the wheels probably got something conductive, right? Or they'll have some kind of chain. I think in this class got some medical people. Do you know that sometimes that trolley, that not trolley, what do you call it? What do you call it? A gurney? What do you call that thing that you put a patient on? Is any one of the medical people here? I'm losing words for this thing. The little trolley that you put people on. So, you know, the thing go down, you got a wheel, you go down there, you got a wheel, and the patient is here lying down, you know? Anybody knows what is the name of the thing, right? A stretcher or something, right? But I'm talking about the part that is rolling on the ground. So sometimes because of the rolling on the ground, charges build up on this stretcher. And if it's too large, let's say you bring a patient and he gets a small electric shock, right? You never know what condition the person come in that could kill them. So they would also, again, put some way, either the wheels got something conductive, right? It will have something where the charge from time to time, when it builds up, will just go down to the earth. It will just go down to the earth, right? So it's a good thing, but it's also a bad thing, right? And there are various ways that people would, you know, make sure that static charges don't build up to the point where you can have a spark jumping across, right? And creating a fire, right? So even with batteries, you have to be careful when you're working with batteries, right? That you don't have, you know, a lot of like petrol spilled all over the place, because when you touch as I was showing you earlier, I was showing you if you have a battery, right? And you got a lug here, and you bring a wire close to it, and then you get a spark, you know, and you bring in the wire close, there's a spark. And if some petrol is spilled here and the vapor is in the air and it ignites, you can cause a big fire, right? So it's very important that you make sure that there's no spillage, right? There's no spillage of petrol about the place or any flammable liquid, ethanol and so methylated, that it will cause a fire, right? I'm looking at our time and I'm saying that, look, I don't want to cram in too much today. I want to leave off at static electricity. And I'll send some notes on the subject. And then later on, maybe Tuesday, we're going to do current electricity. Right? I'm going to send you some notes too. Right? I'm going to send you some notes of almost all that we talked about here. And it's all connected to static electricity, right? Where a charge builds up somewhere, right? Whether be it in the clouds, whether be it in machinery, aeroplane, you know, whatever. And there's that need. I mean, while there are good things like when lightning strikes, you get free fertilizer. Arc welding is made possible by that arcing, you know, or that sparking that is going on, right? Those are the good things. The ionizer in your house, if you have something that does that extract dust from the air in your house, those are the good things. But then this jumping across of that spark, where static electricity created ionization, it causes ionization. And there's that spark, right? It can cause fires. And we want to be, when we're dealing with these things, we have to be safe, right? I don't know, I think one of the boys in this class, they said they work with, machinery and they do welding and so. Is that person here? All right. Yeah, so I want to stop there with static electricity. And the next day we'll take up current electricity. We'll talk about DC current and then we'll talk about AC current.